Yes, so solar thermal. Thought I'd begin with a little bit of context for Australia. And this is a very similar picture to what you'll find in basically any industrialized country these days. So if we look at total final energy consumption, it's about 47% is our industry, and of that, 52% is for heat. And of that, at the moment, 53% is natural gas. But we still have black coal being used for process heat in Australia. Now that we're talking about solar thermal, it's very important to consider the temperature breakdown of the usage. And you can see there that there's quite a lot in that 150 to 250 degrees band. There's also an awful lot in this greater than 600 degrees, and that can be just from calcining and iron and steel and very high temperature processes like that. So looking at the different sectors that are dominant, we've got the alumina sector as a very big user of heat, and theirs is split in sort of 50-50, and some very high temperature calcination, probably hard to abate kind of process, if you will, and a lower temperature digestion thing. We've got oil and gas, significant there, but in a decarbonizing world, you might say, well, where does oil and gas go? Food and beverage is very important. That's dragged up in that analysis by our inclusion of sugar refineries, which are already using a lot of bagasse waste. So when you take them out, it drops down a bit. Iron and steel is an interesting one. And we've got the whole discussion of Australia as a potential exporter of green iron into the future, but that's a very long range story. And then other sectors going on down there with different temperature splits. We do need to think about the economics, and in that regard, we need to think about, well, what are these industry players paying at the moment? And if you look at the yellow bar in the middle, that's to represent natural gas prices. What we see is very large users. First of all, I'll point out that the horizontal axis there is a logarithmic scale of terajoules per year of consumption. And to put that in context, the 1,000 terajoules per year would be like a 40 megawatt thermal use at 80% capacity factor. So 100 is 4 megawatts, 10,000 is 400 megawatts. So very large users, the very, very large 100 megawatt alumina refineries and so on, are effectively paying the wholesale price of gas, which is, let's say, according to that graph, between $10 and $15 a gigajoule, very uncertain. But then the y-axis there is levelized cost of heat. So that's factoring in an approximately 80% conversion efficiency from the gas to the heat, which is why the wholesale price doesn't match the levelized cost of heat. It's rather higher. But what you see is, as you come down to smaller users, they pay more and more. They have to pay distribution and retail costs that the very large users don't. So you kind of get that sort of power law dependence. Now, there are some large users still using coal. That's, of course, cheaper. There's some users who are not connected to the gas network who actually have to truck in LPG and LNG. They tend to be smaller, hence those there. So that's what we're competing against. With solar thermal, Bärbel's already introduced the collector types, but we've got this progression from at one extreme, unglazed flat plate, which is your swimming pool heater on your roof at home, just to sort of warm things up to 60 degrees maybe on a good day. And what we're trying to show here is that as you go from left to right on that graph, you're facing increasing complexity in technology in order to get higher temperatures. So you've got the unglazed flat plate, then our glazed flat plate, the old solar heart systems, but on a more industrial scale, the evacuated tubes, adding a non-tracking mirror, then you've got the troughs or the Fresnel, and finally you've got central receivers or dishes which have the ability to melt ceramic bricks if you really want to. So you can sort of see how that complexity is going to translate to higher capital costs per kilowatt as you seek higher temperatures. So the graph is showing that as linear, but let me just say that's a rule of thumb. It's not exactly linear in a sense. This is a way of thinking about it. But then overlaid on that, what we've got is that this technology, as many other things, has an economy of scale. The bigger systems are more cost effective than little systems. So you've got this capital cost depending on both temperature and size. If we then translate that and look at that, how does that compare with what we're paying for heat from gas or coal or LNG at the moment? We turn our capital costs for the solar thermal technologies into levelized cost of heat. What you can see is you've got this power law effect, the cost effectiveness playing out, that the bigger systems are more cost effective. And interestingly, that whilst it is sort of analogous to the size dependence of the cost of gas, it actually comes down faster. So on the whole, the bigger systems are more competitive than the smaller systems. There's one factor, but then you also see the temperature dependence playing out. And what we see is up to 100 degrees C, more or less, it looks very competitive at all sizes and even competitive against coal. In the 200 and 400 degree bands, there's very good prospects compared to natural gas for users above 100 terajoules per year. At the 600 degrees, with the tower systems and so on, that's still a bit of a stretch, although it's almost touching some competitiveness under certain circumstances. We need to think about where our users are. So the map there tries to show different industry sectors, different sizes, different locations. You see quite a bit around our sort of seaboard, capital cities and so forth. The map on the left is direct beam radiation resources. That's what concentrators care about, the direct radiation, but the map of diffuse radiation looks very, very similar. So what you see is around the East Coast, near the coast, let me flip it around. If you go inland and you cross the Great Dividing Range, the solar resources pick up. If I just do this sort of 1800 kilowatt hour meter squared per year contour on our map, what you can see there is that's sort of the limit for where concentrators kind of make sense. So there's no absolute limit with that. But what you see is there's an awful lot of our country that looks very good for solar thermal, and it's probably not the best choice for Tasmania. But at the 100-degree systems, they look so competitive that we might do them in a much wider array of locations as well. So I thought I'd show a few case studies as well. This one in the winery in Griffith is a really classic one because it's only 200 kilowatts thermal. It's 95 degrees C, and I think really we should seriously look around at the country at a lot more of that sort of installation. There should be a lot of opportunity for that sort of thing. Bärbel already showed this, and it's worth showing just because of its scale, and it's interesting. And what I'd like to point out with this one, make the additional point that this is a combined heat and power system. So you've got a tower system there, which is capable of, huge temperatures, which you don't need because fundamentally they're trying to do desalination and keep a greenhouse warm. But what they're doing is they're using the high temperature steam to do some power generation in a back pressure turbine, then getting the process heat. And that's a very interesting configuration to think about and has its own favorable economics. I would say though that combined heat and power system, the electrical turbine is very much undersized for a 30 megawatt thermal array, but that's just the business decision they made for that plant. I thought I'd show this one as well. It's not Australian, but just because it's so big and just to sort of point out that people have already built solar industrial heat systems on this on a scale that's already big enough for alumina refineries and the really big end of town. It's worth knowing that. My version of Mars Wodonga, which Paul will talk about in a minute. It's very good news indeed for actually the industry globally, but certainly in Australia, to see this progress. And I happened to see, Paul, Dominic Zal showed me this morning, he's got a live, well, there's a live cameras on the site, and they've already started site work. So that's very impressive. You know, a project's real or realer when the site works have actually begun. So I was very impressed with that. So my conclusions: decarbonising process heat is a major challenge. I mean, we all know that. There's a lot of talk about electricity, and the word electricity gets muddled up with energy in some discussions, but end use energy is only 20% electricity and it's 30% heat, and we really have to think about it. When the smaller sites are paying more for their fossil energy. Solar thermal heat is cheaper for large sizes. Solar thermal costs more for higher temperatures. This leads to the economics look pretty encouraging in the 150 to 400 degrees C range, and below as well. Probably avoid our coastal fringes for concentrator systems. No reason that you have to, but the economics won't be as good. And as we've already seen, there's proven systems around the world. This is not new technology. Thank you.